Right now, you're spinning at 1,000 miles per hour, and you can't feel it. But if you stopped, you die in seconds. Close your eyes for a moment. Feel that stillness, that perfect, peaceful calm. It's a lie. Every atom in your body is spinning. The ground beneath you is rotating at speeds that would tear a building apart. The air around you swirls in invisible patterns. Even the emptiness of space itself is turning. Nothing in the universe stands still. Not stars, not planets, not even light itself. And tonight, we're going to discover why. Before we drift into this cosmic mystery, if you're here seeking wonder, a gentle like would mean everything. It tells me these quiet stories still matter, and if you subscribe, you'll never miss another journey through the spinning heart of existence. Now, let's begin with something impossible. In 1922, physicists Otto Stern and Walther Gerlach performed an experiment that should have been simple. They shot silver atoms through a magnetic field to see what would happen. What they discovered shattered everything we thought we knew about reality. The atoms didn't drift randomly. They split into two perfect streams, as if each one was spinning like a tiny top. But here's what haunted them. These particles were spinning without anything making them spin. No force pushed them, no collision started them. They were just spinning. Always had been, always would be. We call this quantum spin. And according to the mathematics discovered by Wolfgang Pauli and later refined by Paul Dirac, every electron in the universe carries this property. It's not that they're choosing to spin, it's that spin is what they are. Think about that. The Stern-Gerlach experiment showed particles splitting into exactly two streams, up or down, nothing in between. It wasn't like watching a spinning top that could point in any direction. These electrons had only two choices, as if the universe itself only spoke in binary. And here's what keeps me awake at night. This quantum spin is an intrinsic property, meaning it's not caused by anything. The electron doesn't start spinning because something hit it. It was born spinning. It will die spinning. It cannot stop. Inside your body right now, there are roughly 7 octillion electrons. That's 7 followed by 27 zeros, and every single one is spinning, not metaphorically, physically, each one carrying a tiny amount of angular momentum equal to exactly h bar over 2, where h bar is the reduced Planck constant. This isn't poetry, it's measurement. But why? Why must they spin? In 1915, a mathematician named Emmy Noether proved something that would change physics forever. She showed that for every symmetry in nature, there must be a conservation law. If the laws of physics work the same way today as they did yesterday, then energy must be conserved. If they work the same way here as they do 1,000 miles away, then momentum must be conserved. And if the laws of physics work the same way regardless of which direction you're facing, then angular momentum must be conserved. Angular momentum. That's the physics term for spin. And Noether's theorem tells us it can never be created or destroyed, only transferred. Think about a figure skater. When they pull their arms in, they spin faster. When they spread them out, they slow down. But the total amount of rotation? That stays exactly the same. The universe follows this rule everywhere. Always, without exception. When stars form from collapsing clouds of gas, they spin faster and faster as they shrink, just like that skater. This is why planetary systems rotate. They inherit the angular momentum from the cloud that birthed them. When galaxies merge, their combined spin redistributes. When particles collide, their rotation exchanges. but the total never changes. This means something profound. The universe has been spinning since its very first moment, and it will never stop.
Let me take you back, not years, not centuries, 13.8 billion years, to the first microsecond after the Big Bang. According to quantum field theory, even in perfect emptiness, there are fluctuations, tiny quantum jitters in the fabric of space itself. And some of those jitters had direction. When cosmic inflation hit, that explosive expansion that made the universe grow faster than light for a brief instant, those tiny rotational jitters were stretched, amplified, frozen into the structure of space-time itself. Scientists now study the cosmic microwave background, the oldest light in the universe, looking for these patterns. And they've found something extraordinary. Quantum fluctuations during inflation formed the seeds for all later structure. Every galaxy, every star, every atom traces back to those primordial quantum jitters. But here's the part that should make you shiver. Some cosmological models propose that primordial spin of the universe can explain how objects acquired the property of spin. Think about what that means. The universe didn't just create particles that happened to spin. The universe itself was born spinning, and every object within it inherited that rotation like a birthright. Your electrons spin because 13.8 billion years ago, quantum fluctuations during cosmic inflation had direction. The galaxy spins because those same fluctuations grew into rotating clouds of matter. Earth spins because it formed from a spinning disk of debris. It's all the same spin, the same ancient momentum, conserved perfectly across billions of years. Take a breath. Let that sink in. Every movement around you, from the stirring of air to the orbit of the moon, is connected to the universe's first moments. Motion is not something that happened later. It was there from the beginning. But if everything must spin, why do most things eventually slow down? That's where the mystery deepens. Here on Earth, friction is everywhere. Roll a ball and it stops. Spin a top and it falls. Every machine eventually grinds to a halt. Entropy always wins. But out there, in the vacuum of space, things are different. The International Space Station orbits Earth at 17,500 miles per hour. It's been doing this since 1998. 27 years of continuous motion, and it's not slowing down. Well, not much. Tiny amounts of atmospheric drag do affect it, but without that, it would orbit forever. The Moon has been circling Earth for 4.5 billion years, never stopping, never needing fuel or maintenance or a push. And deep in interstellar space, the Voyager spacecraft hurtle away from us at 38,000 miles per hour. They launched in 1977. Almost 50 years later, they're still moving at the exact same speed. Because in a vacuum, there's nothing to stop them. Newton's first law. An object in motion stays in motion unless acted upon by an external force. Voyager 1 is currently traveling at about 38,000 miles per hour. It's been doing this for 47 years, and it will keep doing it for millions of years more. Long before Earth is gone, long before the sun has died. Unless it hits something. This is the thing most people don't understand about space. Motion doesn't cost anything. You don't need fuel to keep moving. You need fuel to change your motion, to speed up, slow down, or turn. Once you're moving in a vacuum, you'll move forever. That's why galaxies still spin after 13 billion years, why pulsars rotate 700 times per second without slowing, why electrons never stop orbiting. In the absence of friction, Rotation is eternal.
But wait, Earth isn't in a perfect vacuum. We have an atmosphere, oceans, tidal forces from the moon. So why hasn't Earth stopped spinning? The truth is, it is slowing down, just incredibly, impossibly slowly. Every century, Earth's rotation slows by about 1.7 milliseconds. That's 0.0017 seconds per 100 years. At that rate, it would take about 140 million years for a day to become 25 hours long. Why so slow? Because Earth is massive, unimaginably massive, and massive objects resist changes in motion. This is called rotational inertia. The bigger something is, the harder it is to change its spin. Think about trying to stop a bicycle wheel versus trying to stop Earth. The bicycle wheel you can grab with your hands. Earth? You'd need the gravitational force of the moon pulling on our oceans for billions of years. Which is exactly what's happening. The moon creates tides. Those tides create friction. That friction slowly, gradually transfers Earth's rotational energy to the moon's orbital energy. The result? Earth spins slower, the moon drifts farther away. But even after 4.5 billion years of this, Earth is still spinning. Because that's how much momentum it started with. And here's the beautiful part. The energy doesn't disappear, it transforms. Earth slows down, but the moon speeds up in its orbit. The total angular momentum of the Earth-Moon system? Perfectly conserved. Nothing is lost. Motion just moves. Now, zoom out. Way out. Our Milky Way galaxy is a spiral containing 200 to 400 billion stars, and the entire thing is rotating. Our Sun orbits the galactic center at about 514,000 miles per hour. One complete orbit takes 230 million years, a period scientists call a galactic year. The last time Earth was at this exact position in the galaxy, dinosaurs hadn't evolved yet. The first dinosaurs wouldn't appear for another 20 million years. And the galaxy? It's been spinning for over 13 billion years. How is that possible? Because there's nothing to stop it. In the vast emptiness between stars, there's no friction, no air, no resistance, just gravity holding everything together while momentum keeps it spinning. But here's what's truly mind-bending. The galaxy shouldn't be spinning this fast. When astronomers measure the visible matter, all the stars, gas, and dust, there isn't enough mass to hold the galaxy together at these speeds. The outer stars are moving so fast they should fly away into space. The galaxy should tear itself apart. But it doesn't, because there's something else, something invisible holding it together. We call it dark matter, and it makes up about 85% of all the matter in the universe. We can't see it, we can't touch it, but we can measure its gravitational effect. And that effect is what keeps galaxies spinning for billions of years without falling apart. Dark matter is like an invisible scaffolding, a halo surrounding every galaxy, providing the extra gravity needed to keep everything bound together. Without it, galaxies would unravel in a few million years. With it, they spin stably for billions. And even then, there are further spins to consider.
So now we understand. Things keep spinning because 1. Angular momentum is conserved. 2. Space is mostly empty, no friction. 3. Massive objects have enormous inertia. 4. Dark matter holds galaxies together. But there's still one question we haven't answered. Is there a limit to how fast something can spin? Can anything spin too fast? The answer will terrify you. But wait, if nothing can stop spinning, can anything spin too fast? The answer is yes. And when things reach that limit, reality itself begins to break. In 1967, a graduate student named Jocelyn Bell noticed something impossible on her radio telescope readings. A signal, perfectly timed, pulsing exactly once every 1.337 seconds. It was so precise, so regular, that for a brief moment, her team wondered if they detected an alien civilization. They even nicknamed it LGM-1, Little Green Men. But it wasn't aliens. It was something far stranger. It was a pulsar, a neutron star, the collapsed core of a dead sun, crushed by gravity until it was only 12 miles wide, but containing more mass than our entire sun. And that star was spinning. The pulsar had a period of 1.3373 seconds, but here's what makes it impossible. That 12-mile-wide star weighs as much as our sun. If you took a single teaspoon of neutron star material and brought it to Earth, it would weigh about as much as Mount Everest. When you compress that much mass into something so small and set it spinning, physics breaks down in terrifying ways. Some pulsars spin 700 times per second, 700 complete rotations every single second. The surface of these stars moves at nearly 20% the speed of light. Their gravity is so intense that time itself slows down near them. Their magnetic fields are 1 trillion times stronger than Earth's. And they do this for millions of years, without slowing, without stopping. How? When a massive star dies, its core collapses. In less than a second, matter the size of Earth compresses down to the size of Manhattan. And as it shrinks, it spins faster. Conservation of angular momentum. The same law that governs figure skaters, planets, and galaxies. But neutron stars take this to the extreme. The fastest spinning pulsar known, PSR J1748, rotates at 716 times per second, or 42,960 revolutions per minute. At its equator, it is spinning at approximately 24% the speed of light, or over 70,000 kilometers per second. Think about that for a moment. A star, made of matter so dense that a teaspoon weighs as much as Mount Everest, spinning at 1/4 of light speed. And it's been doing this for thousands of years. But there's a limit. Pulsars should possess enough self-gravity to spin as fast as 1,000 to 1,500 times per second before they break apart. So why don't they spin faster? Why is the record only 716 per second when theory says 1,500 should be possible?
When something spins too fast, physics itself begins to fight back. At extreme speeds, neutron stars start radiating gravitational waves, ripples in space-time itself. These waves carry energy away, gradually slowing the star. It's like trying to spin a ball underwater. The faster you spin, the more resistance you feel. Except in this case, the resistance comes from space-time itself. At a rate of above about 1,000 rotations per second, pulsars would lose energy by gravitational radiation faster than the accretion process would accelerate them. So there's a natural speed limit, not imposed by mechanics or materials, but by the structure of reality itself. And then there's the other limit. If a neutron star were any larger than about 20 miles across, material from the surface would be flung into orbit around the star. Centrifugal force. The same thing that would happen if Earth suddenly started spinning 1,000 times faster. The equator would bulge, mountains would flatten. Eventually, pieces would break off and fly into space. For a neutron star spinning 700 times per second, the surface gravity is almost balanced by the outward centrifugal force.
Any faster, and the star would literally tear itself apart. So the maximum spin isn't a choice. It's a fundamental limit written into the laws of physics. But what happens if you compress even further? What if you squeeze a neutron star until even neutrons can't resist? You get a black hole. And black holes, they spin differently. In 1963, a mathematician named Roy Kerr solved Einstein's equations for a rotating black hole. What he discovered was terrifying and beautiful. A spinning black hole doesn't just pull things in, it drags space-time itself around with it. Imagine dropping a marble into honey while spinning the jar. The honey near the marble starts to swirl, pulling everything nearby into rotation. That's what a spinning black hole does to space and time. This effect is called frame dragging. And near a fast-spinning black hole, it becomes so extreme that nothing can stay still, not even light. There's a region around a spinning black hole called the ergosphere. Within the ergosphere, the dragging is greater than the speed of light, and any observer or particle is forced to co-rotate. Anything within the ergosphere cannot remain stationary relative to a distant observer. They are swept along by the rotating spacetime. Think about what that means. There's a place in the universe where standing still is physically impossible, where space itself is moving so fast that even light must follow its rotation. And here's the strangest part. Particles falling within the ergosphere are forced to rotate faster and thereby gain energy. You can actually extract energy from a spinning black hole, a process called the Penrose mechanism, named after physicist Roger Penrose. A black hole can literally power the universe by spinning. But even black holes have limits. There's a maximum speed for rotation, a point beyond which physics itself breaks down. For black holes, we measure spin using a parameter called A. When A equals 0, the black hole doesn't spin. When A equals 1, it's spinning at the maximum possible rate. And here's the terrifying part. If you make the black hole spin really fast, the ergosphere starts flattening out. This effect causes the event horizon of the black hole to shrink. Eventually, at speed parameter 1 and above, the event horizon converges at the singularity. You get what physicists call a naked singularity, a point of infinite density with no event horizon to hide it, a place where all physical laws collapse and anything can happen. When spin parameter A is greater than 1, there is no event horizon. We have a naked singularity. But nature seems to forbid this. It is impossible to dump more spin into the hole as it becomes extremal. The geometry of space-time itself gets the wrong shape for letting anything in. The universe has a built-in protection mechanism, a cosmic speed limit not just for velocity, but for rotation itself. No matter how hard you try, you cannot make a black hole spin faster than A equals 1. Nature conspires against you. The geometry of space-time itself prevents it. So there is a maximum spin, not because of friction or mechanics or materials, but because reality itself draws a line.
Take a breath. We've journeyed from the smallest electron to the largest black hole, from quantum spin that never stops to cosmic rotation that cannot exceed a limit. And everywhere we look, the same pattern emerges. The universe is built on motion. Spin is not something that happens, it's something that is. But there's one more question, one that brings us full circle. If everything must spin, what happens when rotation meets itself? Two black holes, each spinning at incredible speeds, spiraled toward each other. They'd been orbiting for millions of years, gradually getting closer, moving faster, and then they touched. The collision lasted less than a second, but in that brief moment, they released more energy than all the stars in the observable universe combined. That energy rippled outward as gravitational waves, literal waves in the fabric of space-time itself. And 1.3 billion years later, those waves reached Earth. The two detectors of the Laser Interferometer Gravitational Wave Observatory detected a signal from GW 150914 on September 14, 2015. LIGO estimated that the peak gravitational wave power radiated during the final moments of the black hole merger was more than 10 times greater than the combined light power from all the stars and galaxies in the observable universe. The collision converted about 3 solar masses worth of matter into gravitational wave energy. 3 times the mass of the Sun converted into pure energy in less than a second. The resulting black hole? A rotating Kerr black hole with a spin parameter of 0.68. That's 2/3 of the maximum possible angular momentum for its mass. 2 spinning black holes merged and created an even faster spinning black hole. Their rotation didn't cancel out. It combined, added together, conserved. Because that's what angular momentum does. It persists, it transfers, but it never, ever disappears. Since that first detection in 2015, LIGO has detected dozens more black hole collisions, each one a cosmic dance of rotation, ending in merger, producing gravitational waves that travel across the universe at light speed. Each one proving the same fundamental truth. Spin is eternal. Even when objects collide, even when they merge and transform, the rotation continues. The universe has been spinning for 13.8 billion years, and it will keep spinning until the very end of time itself. Take a slow breath. Feel that stillness again, that perfect calm. Remember, it's an illusion. You're spinning. The Earth is spinning. The galaxy is spinning. And somewhere right now, 1.3 billion light years away, 2 black holes are spiraling toward each other, faster and faster, about to release more energy in 1 second than all the stars in the universe combined. The cosmos is alive with motion. And you are part of that eternal dance.
We've discovered that everything spins, from electrons to galaxies, from atoms to black holes. But we haven't answered the deepest question: why can't anything stop? What force keeps the universe in motion? What law forbids stillness? The answer is simpler and stranger than you might think. Here's something that will change how you see reality. The universe never forgets. Every motion that has ever occurred is still recorded somewhere, not in a book or a computer, in the fabric of space-time itself. This is what conservation laws really mean. They're not just rules, they're memory systems. When angular momentum is conserved, it means the universe remembers every rotation that ever happened. The total spin of the universe at the Big Bang equals the total spin of the universe today. Nothing is lost, nothing is created, it just moves around. Think about it like this.
Imagine you have 100 coins. You can move them from pocket to pocket, give some away, receive some back. But the total number of coins in existence never changes. Angular momentum works the same way. The universe started with a certain amount of spin. That exact same amount exists today. It's just distributed differently. Your electrons are spinning with momentum that was there 13.8 billion years ago. The Milky Way rotates with angular momentum inherited from quantum fluctuations during cosmic inflation. Every spin you see today is ancient, prehistoric, primordial. The universe doesn't create new motion, it just redistributes the motion it was born with. On Earth, we live surrounded by matter. Air molecules constantly bump into us. Friction is everywhere. Energy dissipates as heat. But space is different. In the vast emptiness between stars, there's essentially nothing. Maybe 1 atom per cubic meter, sometimes less. And in that emptiness, motion becomes eternal. When there's nothing to collide with, nothing to create friction, motion just continues forever. This is why satellites don't slow down, why asteroids travel for billions of years at constant speed, why galaxies rotate for eons without stopping. Friction isn't a fundamental law, it's an environmental condition. Remove the environment and motion becomes permanent. Here's a thought experiment. If you could remove every single atom from around a spinning object, create a perfect vacuum, that object would spin forever. Not billions of years, forever. Literally eternal motion. And that's essentially what space is. A near-perfect vacuum where motion never dies. The universe is a friction-free system, and in such a system, rotation is immortal. But there's something deeper happening here. Something that goes beyond just no friction. It's about symmetry. Emmy Noether's theorem states that every symmetry in physics corresponds to a conservation law. And this isn't just a neat mathematical trick, it's a fundamental description of reality. Time symmetry, energy conservation. Space symmetry, momentum conservation. Rotational symmetry, angular momentum conservation. What does rotational symmetry mean? It means the laws of physics don't care which direction you're facing. North, south, east, west, physics works the same way.
And because the universe has this rotational symmetry, angular momentum must be conserved. It's not that the universe chose to conserve angular momentum, it's that the very structure of reality, its geometric symmetry, demands it. You can't have rotational symmetry without angular momentum conservation. They're the same thing, expressed differently. So when we ask, why can't things stop spinning? The answer is, because the universe itself is rotationally symmetric. And in a rotationally symmetric universe, spin must be eternal. Here's where it gets really strange. Time and rotation are connected in ways most people never realize. Think about how we measure time. The Earth rotates, that's a day. The Earth orbits the Sun, that's a year. Ancient civilizations used the Moon's orbit to mark months. We use the oscillation of cesium atoms to define seconds. Every measurement of time is actually a measurement of rotation. Clocks don't measure some abstract flowing river of time. They count cycles, rotations, vibrations, motion. An old-fashioned clock has gears that spin. A pendulum swings, circular motion. A quartz watch measures crystal oscillations. An atomic clock counts electron transitions. All of it is rotation. So in a very real sense, time is rotation, or at least time is how we perceive rotation. This gets even stranger near massive spinning objects. Einstein's general relativity predicts that rotation can actually affect the flow of time itself. Near a spinning black hole, time runs at different speeds depending on how the rotation affects spacetime. This is called frame dragging, and it's been measured.
In 2004, NASA launched Gravity Probe B, a satellite carrying ultra-precise gyroscopes. Its mission? Measure how Earth's rotation drags space-time around with it. And it worked. They detected the frame-dragging effect. Earth's rotation literally twists time itself. So rotation doesn't just happen in time. Rotation creates time, or at least shapes how time flows. Without rotation, would time even exist? Some physicists argue that in a universe with no motion, no change, no rotation, time would be meaningless. Time is change, and rotation is the universe's most fundamental form of change. Now let's go smaller, all the way down to quantum mechanics. Remember quantum spin, that intrinsic angular momentum every particle has? Here's what most people don't realize. Quantum spin isn't just a property particles happen to have, it's fundamental to what particles are. In quantum field theory, particles are described by their quantum numbers. These numbers define the particle's identity. For electrons, charge equals -1, spin equals 1/2, mass equals 0.511 MeV. That spin value isn't describing the electron's motion, it's describing the electron's existence. An electron with spin 1/2 is fundamentally different from a hypothetical particle with spin 1/3. They're not the same particle spinning differently, they're completely different particles. This is why electrons can never stop spinning, because an electron without spin wouldn't be an electron. It would be something else entirely. It's like asking, can you remove redness from red? You can't. Red is redness. An electron is spin 1/2. And here's the truly mind-bending part. This quantum spin is what makes chemistry possible. The Pauli exclusion principle states that no two electrons can occupy the same quantum state. This is only possible because electrons have half-integer spin. If electrons didn't spin, atoms couldn't exist. Chemistry wouldn't work. Molecules couldn't form. Life requires proteins. Proteins require molecules. Molecules require atoms. Atoms require electron shells. Electron shells require the Pauli exclusion principle. The Pauli exclusion principle requires spin. So in a very literal sense, life exists because particles spin. Remove spin from the universe, and you remove matter as we know it.
Take a breath. We're starting to see the full picture now. Things can't stop spinning because 1. Angular momentum is conserved. 2. Space is a vacuum. 3. Rotation defines time itself. 4. Spin is fundamental to particle identity. 5. Without spin, matter cannot exist. But there's one more layer. One final secret. If the universe started with spin, where did that spin come from? Let's go back to the very beginning, before stars, before atoms, before even light itself, the Planck epoch. At this moment, the universe was smaller than an atom. Temperature? Infinite. Density? Infinite. The laws of physics as we know them didn't exist yet. And yet, something was already spinning. How do we know? Because of quantum fluctuations. In quantum mechanics, even perfect emptiness isn't truly empty. Virtual particles constantly pop in and out of existence. Fields fluctuate randomly, and some of those fluctuations have angular momentum. During cosmic inflation, that brief period when the universe expanded faster than light, those tiny quantum fluctuations were stretched to cosmic scales. The tiny spins became galactic spins. The quantum angular momentum became the rotation of everything. And here's the key. Those fluctuations didn't violate conservation of angular momentum, because in quantum mechanics, particles can appear in pairs with opposite spins. Total angular momentum? 0. One particle spins clockwise, the other counterclockwise. They cancel out. The universe's total spin remains 0.
But locally, in our region of space, there's a preference, a bias, a direction. And that bias became the rotation of galaxies, stars, and planets. So the universe as a whole might have zero total spin, but within it, everything is spinning in different directions, with all that motion ultimately canceling out. It's like a room full of spinning tops. Each one rotates, but the total angular momentum of the room is zero because they're spinning in different directions. The universe works the same way. Here's a terrifying thought experiment. What if somehow everything stopped spinning at once? What would happen? First, electrons would cease to exist. Remember, spin defines what an electron is. Without spin, they'd collapse into something else, something that can't form atoms. All matter would disintegrate. Second, atoms couldn't maintain their structure. Electron shells depend on angular momentum. Without it, electrons would either fall into the nucleus or fly away. Chemistry would end. Third, planets and stars would lose their shape. Rotation creates the centrifugal force that partly counteracts gravity. Without it, everything would collapse inward. Earth would compress, the sun would shrink, black holes, well, they'd probably become even stranger. Fourth, the galaxies would tear apart. The delicate balance between rotation and gravity would break. Stars would either fall toward the center or fly off into space. And fifth, and this is the strangest part, time might stop. If time is fundamentally connected to rotation and all rotation ceased, would time itself freeze? We don't know. The math breaks down. Physics can't describe a universe without angular momentum because no such universe could exist given our laws. But here's the thing. This scenario is impossible. Not improbable, impossible. Conservation of angular momentum isn't a suggestion, it's a law. And laws in physics are absolute. You cannot remove angular momentum from the universe. You can only move it around. So everything will keep spinning, not because it wants to, not because something is making it, but because the mathematical structure of reality demands it.
Imagine hearing a voice say, "Everything around you is spinning, while nothing you can see is moving at all." Your walls sit still, the floor feels anchored, your body feels steady. No dizziness, no tilting, no sensation of motion. Yet this perception is a trick. Stillness is a costume the universe wears because human senses are primitive instruments. We evolved to notice predators in grass, not the rotation of reality. If our biology were better tuned, we would feel it. An endless turning beneath our feet, a drift through space, a spiral through the galaxy, and a rotation embedded so deeply into existence that even the particles in your bloodstream are spinning right now. The Earth rotates once every 24 hours, but that's just the first layer. The planet orbits the Sun at a staggering velocity. The Sun itself orbits the center of the Milky Way. The Milky Way rotates through the cosmic web, an immense scaffolding of dark matter and galaxies stretched across the cosmos like a woven lattice. And that entire cosmic structure is not static. It twists, it curls, it flows. Everywhere we look, rotation appears, not as a rare occurrence, but as a universal signature. It's not the exception, it's the rule. And yet think back to school. Think back to lectures, diagrams, charts, glossy textbook illustrations. We were told that things spin, but never why. We memorized rotation periods and orbital mechanics, but the fundamental question, the one that actually matters, was never placed on the desk. Teachers explained the speed of Earth's rotation, but not the cause. Documentaries showed galaxies pinwheeling through space, but never paused to ask why motion persists.
Science channels demonstrated angular velocity with polished graphics, but never acknowledged that the existence of rotation at all is one of the deepest mysteries in physics. Because when we ask why things spin, we immediately uncover a contradiction. On Earth, everything eventually stops moving unless something keeps pushing it. Wheels slow down, tops wobble and fall, gears lose momentum, swings lose height, rivers slow. Friction eats motion. Drag consumes energy. The world we see teaches us that movement fades. And so, logically, the universe, vast, ancient, and unimaginably old, should have slowed to a halt by now. But it hasn't. Planets haven't stopped spinning. Stars haven't stopped spinning. Galaxies haven't stopped spinning. Even the quantum particles that make up your body, electrons, quarks, neutrinos, haven't stopped spinning. They spin eternally. They spin without friction. They spin without a mechanism draining away their motion. This is not how motion behaves in our everyday world. This is something else entirely. Something immune to decay. And that should make us uneasy, because it suggests that rotation isn't just an accident of cosmic history. It isn't leftover debris from an early explosion. It isn't the residue of some ancient swirl. The deeper we look, the more we see that spin is woven into the blueprint of existence itself. It isn't a side effect, it's fundamental. So the first crack in the illusion forms. If everything spins, and spin never fades, then motion in the universe is not like motion on Earth. It obeys different rules, rules that don't care about friction or resistance or decay. Rules that seem almost supernatural from a human perspective because we never encounter them in our daily lives. And once that realization settles in, the next question rises like a chill. If everything is spinning, who or what started the motion? Because motion requires a cause, right? Push a ball and it rolls. Stop pushing and it slows. So what pushed the universe? What hand, what force, what initial shove set planets rotating, stars spiraling, galaxies twirling like titanic whirlpools of light? This is where most people expect an answer involving the Big Bang. But here's the twist no one tells you. Even the Big Bang doesn't explain the origin of spin. An explosion, if that's even the right word, does not automatically produce rotation. If the universe began in a perfectly symmetrical state, there should have been no preferred direction, no twist, no angular momentum at all. And yet, here we are, in a universe filled with spinning structures, from the smallest particles to the largest cosmic formations. So either, 1, the universe was born spinning, 2, spin emerged from a deeper rule of physics, or 3, we are missing something enormous. This is where curiosity turns into tension. Because if the universe didn't start spinning, then something happened afterward that created rotation everywhere. But if the universe did start spinning, then we are forced to ask a far stranger question. What was the universe spinning relative to? Spin requires a reference frame. Rotation is only meaningful if there is something to rotate against. There should be no outside to the universe, no external backdrop, no cosmic turntable. And yet, the motion is real. This is why the question feels forbidden. Not because anyone hid it, but because once you ask it, reality starts to feel unstable around the edges. The moment you notice the crack, you can't unsee it. You start to realize the universe is behaving like a machine whose gears have always been turning, but whose power source is nowhere in sight. And here comes the final push of this opening revelation. Spin is not just motion. Spin is identity. Spin is structure. Spin is the reason anything exists at all. Remove rotation, and atoms fall apart. Remove rotation, and matter collapses into something unrecognizable. Remove rotation, and time itself may lose meaning. So when we ask why the universe spins, we are not asking a curiosity. We are asking why the universe exists. This is the doorway into the deeper mystery, the opening of the story, the threshold the viewer crosses before the descent into the stranger, darker, more breathtaking truth that follows. Because if spin can't stop and spin can't be removed, then the universe is not just spinning. It is compelled to spin. And now we have to find out why. If we want to understand why the universe never stops spinning, we must confront one of the most quietly astonishing truths in physics, a principle so fundamental that it governs the motion of galaxies, the structure of atoms, and the behavior of your own body without you ever noticing it. It's called conservation of angular momentum, but that phrase doesn't capture its weight. The more accurate description is this: once rotation exists in the universe, it can never truly be erased. Angular momentum is not like energy in a battery that can drain, fade, or dissipate. It's not like heat that spreads and evens out. It's not like motion that slows with time in our everyday world. Angular momentum is permanent, stubborn, untouchable. It can change form, move from one object to another, speed up, slow down, or redistribute, but it cannot vanish. The universe treats it as sacred. A skater spins faster by pulling their arms inward, not because they exert more effort, but because the universe enforces a trade-off. A collapsing star spins faster for the same reason. When something becomes smaller, its rotation accelerates. When it spreads outward, it slows. Planets form from swirling disks because matter falling inward must spin faster as it contracts. Even the orbits of moons and rings reflect this same rule. Angular momentum is the invisible accountant of the cosmos. Nothing escapes its bookkeeping. But this law doesn't just describe motion. It arises from something deeper, something philosophical, something almost metaphysical. The universe has no preferred direction. This is what physicists call symmetry, specifically rotational symmetry. Space looks the same no matter which way you turn. There's no cosmic north, no cosmic up, no master compass. And because space has no chosen orientation, rotation must be conserved. The rule is not arbitrary. It is the mathematical shadow cast by the structure of space itself. If space did have a preferred direction, angular momentum could fade, spin could evaporate, rotation could stop. But because space is directionless, spin becomes eternal. This is a moment where physics reveals its poetry. The emptiness of space, the absence of direction, is what forces all spinning things to keep spinning forever. But the story gets stranger when we zoom in. At the level of atoms, angular momentum isn't just a property of motion. It becomes a defining characteristic of existence. Particles don't just spin like miniature planets. Their spin is intrinsic, fundamental, non-negotiable. Electrons have a spin quantum number of 1/2. Photons have spin 1. Gluons, quarks, neutrinos all carry specific spin values that determine how they behave, how they combine, how they form matter.
If you changed the spin of an electron, even slightly, it would stop being an electron. It would become a different particle entirely. Spin defines identity. Spin is like a fingerprint written into the laws of physics. Without it, atoms would collapse, chemistry would fail, and reality would dissolve into something unrecognizable.
Spin is the scaffolding that holds existence together. So the mystery deepens. If spin defines matter, and angular momentum cannot be destroyed, then we aren't just dealing with a law of motion, we are dealing with a foundation of reality. Remove gravity and the universe reconfigures. Remove electromagnetism and atoms fall apart. Remove spin and the universe ceases to exist at all. This realization forces a new question into view. Where did the universe get its angular momentum in the first place? Because if angular momentum can never be removed, then the total amount present today must be the same amount that existed at the beginning of time. But that creates a paradox. If the universe began in a perfectly uniform state, no direction, no irregularities, no rotation, then there should have been no angular momentum to conserve. There should have been nothing to preserve. And yet here we are in a universe filled with spinning planets, stars, galaxies, and particles. Scientists tried to solve this by proposing that perhaps all the spinning objects balance out. Maybe for every star rotating one direction, another spins the opposite way. Maybe angular momentum sums to zero overall. But this doesn't solve the deeper issue, why there is spin locally at all. If the universe began in total symmetry, there should be no reason for rotation to exist anywhere. So another theory attempts to answer it: turbulence in the early universe. But turbulence requires a medium to move through, something like a fluid or gas. In the earliest universe, such a medium did not exist. Space itself was emerging. There was nothing to churn, nothing to twist, nothing to rotate. Another explanation claims rotation is simply a leftover remnant from the Big Bang. But again, explosions do not automatically produce spin. If a firework detonates symmetrically, it expands without rotation. If the Big Bang were perfectly symmetrical, the universe should have expanded without spin. And yet, rotation is everywhere. So the question persists, growing sharper, heavier, more uncomfortable. Why is the universe full of spin if nothing should have caused it? This is where physicists turn to an even deeper layer of reality, the mathematics of quantum mechanics. At the smallest scales, motion exists even when nothing is moving. Particles have angular momentum even when they are not rotating in any classical sense. Spin becomes a built-in feature of the quantum world, not something acquired. But this only pushes the mystery backward. If quantum spin is fundamental, then it existed before matter formed. If it existed before matter formed, it existed before atoms. If it existed before atoms, it existed before space had structure. So spin reaches all the way back into the very first instance of the universe. This is where the question becomes almost philosophical. Is spin a property of the universe, or is spin a requirement for a universe to exist at all? Because if a universe without spin is impossible, if matter cannot exist without angular momentum, then spin might not have emerged after the universe began. It might have been present at the moment of creation because a universe without it could never have formed. And this leads to the most profound implication yet. The universe spins not because something set it spinning, but because a universe that wasn't spinning could never have existed. This is not just a physical claim, it is an existential one. Spin is not merely motion, it is the condition that allows structure, identity, separation, and time. A universe without spin is a universe without form, without atoms, without stars, without thought. Angular momentum is the hinge that allows reality to unfold. So now we stand at the threshold of an even stranger idea, that if spin never began and can never end, then angular momentum may be eternal, not just in duration, but in essence. Something older than time, something deeper than matter, something the universe inherited rather than generated. And that realization brings us to the edge of the next revelation, the moment before motion, the instant where space, time, and physics themselves begin to flicker into existence. Because if spin didn't start with planets, and didn't start with stars, and didn't start with matter, then we must follow it back to the only place left.
To trace the origin of spin, we must travel into a region of reality where human intuition collapses, where mathematics trembles, and where language barely functions. We have to return to the earliest sliver of existence, the moment when the universe was not a vast expanse, but a seething, compressed storm of potentiality, smaller than a proton, hotter than a star's core, denser than anything we can imagine. This era has a name, whispered in physics with equal parts reverence and frustration: the Planck epoch. This is the first 10 to the minus 43 seconds after the universe came into being. Not a millisecond, not a nanosecond. A time so short that if you tried to write it out, it would disappear beneath zeros stretching across a page. In that infinitesimal moment, the four forces of nature had not yet separated. Space and time had not stabilized. There were no particles, no light, no atoms, no emptiness, because even emptiness had not yet been defined. Reality was a quantum haze of fluctuating fields, chaotic and uncertain, where probability ruled and nothing could be pinned down. And here is where we uncover the next revelation. Even in this primordial chaos, there was motion. Not classical motion, not objects spinning through space. Space itself didn't exist in the way we understand it. Instead, there were fluctuations, tiny, spontaneous variations in energy and fields. Quantum mechanics says these fluctuations are unavoidable. The universe cannot be perfectly still. A perfect vacuum cannot exist. Stillness violates the uncertainty principle. Silence is forbidden. And among these fluctuations were variations that carried angular momentum, not because they were pushed, not because anything set them turning. They existed because the equations of quantum mechanics demanded that fluctuations come in all possible forms, including those with spin. This is the first crucial insight. Spin predates structure. Before atoms, before forces, before time flowed smoothly, spin was already there in microscopic, jittering fragments of proto-reality. Then something happened that changed everything. Inflation. Inflation is not expansion in the way a balloon inflates. It is space itself stretching, faster than the speed of light. Not because objects outran light, but because the fabric they sat upon expanded beneath them. In a fraction of a moment, these tiny quantum fluctuations were stretched to astronomical scales. Ripples became waves. Waves became vast patterns. Tiny rotations were magnified far beyond their original scale. And here lies the second crucial insight. Quantum spin became cosmic spin. The rotation of galaxies, stars, planets, and disks, these are not coincidences. They are the fossilized remains of the earliest quantum disturbances, enlarged by inflation into the scaffolding of cosmological motion. But doesn't this violate conservation of angular momentum? No. And here is the subtlety most people miss. Quantum fluctuations appear in pairs with opposite angular momentum. One spins clockwise, the other counterclockwise. Together, they sum to zero. This means the total angular momentum of the universe may still be exactly zero, even though everything within it is spinning. It's a cosmic balancing act, a universe filled with motion, yet motionless in total. This is the third insight. The universe can be globally still while locally spinning everywhere. It is like a room filled with tops, all spinning in different directions. The room has no net rotation, but motion is everywhere within it. This idea is unsettling because it means our intuitive understanding of rotation is incomplete. Spin does not require a background. It does not require an external frame. It can exist in a self-contained system as long as everything balances. And now we reach a deeper implication.
one most people never consider. If spin originates from quantum fluctuations, then spin was not created. It emerged from the fundamental instability of nothingness. It was not introduced. It was inevitable. Which leads to an even staggering idea. A perfectly motionless universe is impossible. Quantum mechanics forbids it. The laws of physics require that even nothing must fluctuate. Stillness is not allowed. Zero is unstable. The universe did not begin with order, but with restless possibility. This shifts the narrative entirely. Instead of asking what set the universe spinning, we must ask, why couldn't the universe avoid spinning?
Because if quantum fluctuations always exist, and if fluctuations inevitably include angular momentum, and if inflation magnifies those fluctuations into cosmic scale motion, then rotation is not a mysterious leftover. It is an unavoidable consequence of the universe coming into being. But there is still one more layer, darker and stranger. Time itself may be tied to spin. Not metaphorically, not poetically, literally. In quantum field theory, spin determines how particles transform when space rotates. Spin dictates symmetries. Symmetries dictate conservation laws. Conservation laws dictate the flow of time. If you remove spin from the equations, time loses its mathematical anchor. Events lose sequence. Cause and effect unravel. Temporality dissolves. So now we face a fourth insight. If there were no spin, there may be no time. And if there is no time, there is no evolution, no unfolding, no becoming. The universe cannot expand, cannot cool, cannot form stars, cannot produce minds capable of asking questions about its origins. Spin is not a detail. It is the hinge on which reality swings. At this point, the mystery turns inside out. Instead of wondering how spin appeared, we begin to understand that spin is the reason anything happened at all. The quantum fluctuations that seeded angular momentum also seeded density variations. Those variations became galaxies, stars, planets, continents, bodies, thoughts. Which brings us to the final and most unsettling realization of this chapter. Spin may be the first structure the universe ever had. Before mass, before light, before time flowed, before space expanded. Spin may have been the first thing that could be said to exist. And if that is true, then everything, your body, your memories, your awareness, is an echo of that first rotational instability. You are made of particles that have never stopped spinning since the first moment of time. The rotation in your atoms is a direct descendant of the fluctuations that existed before there were atoms to contain them. We do not merely live in a spinning universe. We are built from its spin. And now the stage is set for the final and most unsettling question. If spin cannot be destroyed, if spin existed before matter, if spin gives rise to time and structure, what would happen if all spin stopped? This leads us into the final chapter, the forbidden scenario, the impossible universe, the thought experiment that reveals what spin truly is. To understand the true meaning of spin, we have to perform a forbidden experiment. Not in a lab, but in imagination. We have to envision a universe where rotation, angular momentum, and spin do not exist. Not slowed, not cancelled, not reduced, removed. A universe where nothing turns, nothing twists, nothing curls, nothing orbits, nothing cycles. A universe without galaxies spiraling, without planets circling stars, without atoms rotating in probability clouds, without particles possessing intrinsic spin. First, strip away all cosmic rotation. Galaxies would not form their spectacular spirals. Without angular momentum, dust and gas clouds would collapse straight inward under gravity with no stabilizing centrifugal balance.
Stars would ignite briefly and then collapse into black holes with astonishing speed. No planetary systems would form because planets only coalesce inside rotating disks. Without disks, no planets. Without planets, no worlds. Without worlds, no oceans, no continents, no weather, no biology, no eyes to witness the sky. But the unraveling does not stop there. Now we remove rotation at smaller scales. Atoms, as we know them, cease to exist. Electrons do not orbit like planets around a star, but their behavior is still governed by quantum angular momentum. Without this property, electron shells collapse. Chemistry dissolves. Matter itself loses structure. Everything becomes a uniform smear, a featureless cloud of undifferentiated energy. No molecules, no carbon chains, no proteins, no DNA, no cell membranes, no neural networks, no minds. Still we go deeper. Particles themselves lose identity. Spin is one of the essential quantum numbers that define what a particle is. Electrons have spin 1/2, photons have spin 1, gravitons, if they exist, have spin 2. These values determine how particles obey statistics, how they stack, how they combine, how forces propagate. If spin is removed, fermions and bosons, the two great categories of existence, cease to be distinct. Matter and force become indistinguishable. Physics collapses into incoherence. Then we reach the deepest level. Without spin, symmetries break. And without symmetries, conservation laws evaporate. Energy conservation, momentum conservation, the invariance that allows the universe to behave consistently, they crumble. Time itself becomes undefined. Not time ending, time meaning nothing. Without spin, there is no arrow, no direction, no flow, no before, no after. A universe without spin is not a universe frozen in stillness. It is a universe that cannot be. So here is the stunning truth revealed. Spin is not something the universe has. Spin is something the universe is.